Welcome everyone. Today we are going to start on chapter 8, which is, if you're in my fall and spring class, our last major topic that we're going to cover. Again, if you're in my short form classes like a mini-mester or summer class, we do have chapter 10, which is regression and correlation, but for the fall and spring classes, chapter 8 and chapter 9 are both on hypothesis testing, and that's our last major topic. So we're going to start with section 8.1 today, which is on the steps in hypothesis testing, and we're going to be talking about the traditional method of hypothesis testing. There's three kind of basic, commonly used methods for hypothesis testing. We're only going to do the traditional method, but there's also what's called the p-value method, and then that you can use confidence intervals actually to do hypothesis testing also. But we're going to do what's known as the traditional method. So in this section, we're going to first talk about just the definitions and what a hypothesis test is in general. We're going to learn to state the null and the alternative hypothesis. We're going to learn how to find the critical values for the z-test, which is off of the same table that we've been using, that we were using for confidence intervals, so that should be pretty comfortable. And then we're going to learn the 5 steps used in hypothesis testing. So in the traditional method, and also in the p-value method actually, there's 5 steps, and we're going to talk about those 5 steps in section 8.1. And then in section 8.2, we'll actually get into doing a hypothesis test. All right, so first of all, what is a hypothesis test? And when I say that, and then you look at the table and you start reading the labels, you'll notice that it's talking about a jury and a defendant and innocent and guilt, and you're like, wait a minute, did she get the wrong slide in here? And the answer is no. What we're going to do is we're going to use a trial court as an analogy for hypothesis testing, because the concept of a trial is very similar to what we're doing with a hypothesis test. So we're going to start by talking about how things can come out, what the outcomes are in a trial. So in a trial, we have the jury's decision, and we also have the defendant's true status. So when you take someone to trial, you put them on trial, you charge them with something, that doesn't change the truth of what happened. By taking them to trial, it doesn't change whether they actually did whatever crime they're being charged with or didn't do whatever crime they're being charged with. What the trial does is it's trying to find out the truth. We're trying with the trial to determine if there is enough evidence to show that they committed the crime or if there's not enough evidence. So the trial, you're taking someone and you're charging them and you're saying, I'm going to present the evidence that I have, and with that, we're going to make a decision. But the truth is out there somewhere. They either did the crime or they didn't do the crime, in the most basic sense. I know there's some nuances to that, but in the basic sense, they either did or did not. So, hold on one second, I want to get some different colors here. Okay, so when the jury comes back with a decision, if the truth is that the defendant was innocent, what would we hope that the jury came back with as a decision? Well, we would hope that the jury would come back with a not guilty decision. If they're innocent, we would hope they would come back with a not guilty. They would say, there was not enough evidence, you did not prove your case, prosecutor, we're going to come back with a not guilty decision. Okay? So this is a correct decision. if the defendant is truly innocent, we hope that the jury would come back with a not guilty. However, if the defendant is guilty, we would hope that the jury would also come back with a guilty verdict. So if the truth is, remember this is the true status, if the true status is that the defendant did do the crime, then we would hope that the jury would come back with a guilty decision. So a decision of guilt. So both of these decisions are correct. If they're innocent, we would hope that they were found not guilty. If they're guilty, we would hope that they were found guilty. So let me clean this up a little bit. And now let's talk about the other things that could happen. If a defendant is innocent and the jury comes back with a guilty verdict and says, we think this defendant is guilty, we think that the prosecutors had enough evidence to show that this defendant is guilty, and they come back with that guilty verdict, but in fact, the true status was that they were innocent, then that is an error. That's a mistake. Okay? I think everybody, we don't want anyone who's innocent to be found guilty and have a punishment for something they didn't do. On the other hand, it's not ideal if someone is not found not guilty when the truth of the matter was they were guilty. So if the truth is that they were guilty, but the jury comes back with a not guilty verdict, that's also an error. That means that the person did commit the crime, but the prosecutor did not present enough evidence to convince the jury beyond a reasonable doubt that they committed that crime. And so, not necessarily saying that the jury made a mistake or even that the prosecutor made a mistake, just that there's not enough evidence shown to come back with the correct decision, because the correct decision, if someone is guilty, you would hope that they would be found guilty. So, in our legal system, and this is ideal, I know it's not always ideal, but in our legal system, we err on the side of caution a bit, caution for the individual. So our legal system is set up, is meant to favor the individual. We have the innocent until proven guilty. Or innocent until enough evidence shows that you're guilty. So innocent until proven guilty is kind of our motto. Meaning that a person is supposed to be presumed innocent until someone can prove that they're guilty. And so that errs on the side of the individual, meaning that we consider in our justice system, again, ideally, that finding someone who's innocent, guilty, and sending them to jail when they didn't do anything is a worse type of error. Or I call that a type 1 error. Now, the other is still an error. It's still bad when somebody who's guilty is found not guilty and goes free, even though they did the crime. But we consider that a lesser error. That we would rather someone that's guilty be found not guilty than to send an innocent person to jail or whatever other punishment. So now, remember, we have a defendant, we have a decision. Sometimes that decision is correct, sometimes it is an error. We're going to apply that now to our hypothesis testing. So in hypothesis testing, and I have this, that same trial one here in a little bit smaller form here so we can compare. So just like in a jury trial, there are 4 possible outcomes when we're talking about a hypothesis test. So we have a hypothesis test and there are 4 possible outcomes. There's a true situation and there's a decision that needs to be made. So in our hypothesis test, we are taking what's known as the null hypothesis. This little h sub 0 is called the null hypothesis. You can think of it as H for hypothesis, and you can either think of it as nothing has happened, or you can think of it as the original hypothesis, like an O, but it's like the starting place with our hypothesis test. And we're going to take that null hypothesis, that null starting point, and take it to trial. Now, just like with a court trial, when you take that null hypothesis to trial, you run a test on it, a hypothesis test, there is a reality. The null hypothesis is either true or it's false. So our original starting hypothesis is actually really true or it's really false. There is a true answer to that. The problem is we don't always know whether it's true or false. So we're taking it to trial to see if we can come up with enough evidence to make a decision as to whether we think it's true or false. So the null hypothesis is our little defendant, okay? When we're done with the hypothesis test, we're going to make a decision. We're going to make a decision to not reject the null hypothesis or reject. You notice that's kind of the same terminology that we use in a trial. They don't come back with innocent or guilty. They say they're not guilty or they're guilty. Same thing with a hypothesis test. We're either going to say we're going to not reject, which means there was not enough evidence, or we're going to reject, which means there's enough evidence. Okay, let me write this up here. So if we do not reject, that means there was not enough evidence. If we do reject, that means there was enough evidence in our statistical testing. So there was enough evidence to reject the null hypothesis or find the null hypothesis guilty, or there was not enough evidence, and so we do not reject it or we do not find it guilty. And just like with the trial, if we have a null hypothesis that was true, get this all cleared out here. Okay, so if we have a null hypothesis that was actually true, we would hope that our test would not reject the null hypothesis. That would be a correct decision. On the other hand, if the null hypothesis was false, we would hope that our test, our hypothesis test, would reject the null hypothesis, would say, you're guilty, you're false, we don't believe you. And that would be the correct decision. Rejecting the null hypothesis, if it's false, would be a correct decision. And then, on the other hand, if we have a null hypothesis that is true, and our test comes back and rejects it, now we've taken information that was actually true and put it into question. So we've taken data or decision or information and we've said, we think you might be wrong, and we find enough evidence and we reject it, and yet it was actually true. That's considered a worse error. That's considered a type 1 error when the null hypothesis, the starting base information, was actually true and we reject it. That's a type 1 error. Then if it was false and we do not reject it, that's a type 2 error. That's still a mistake, but it's not quite as bad. We're kind of where we started. We're back to where we are saying, okay, well, I don't have enough evidence to prove it, so I'm going to not reject it. I'm going to accept that the null hypothesis must have been okay, even though it was false. But we're kind of back to the starting block. Whereas if we reject a null hypothesis that was actually true, now we've put good data into question, which is considered a worse type of an error, type 1 error versus a type 2 error. So just to kind of give you an idea where we're going with this, the null hypothesis is kind of the I like to call it the status quo. So information that's already been collected about some data and put out there, and the null hypothesis is, well, this is what was said before, this is the status quo, where are we going to go from there? So we have that status quo, and we're going to try to take it to the test and decide whether to reject it or not reject it. So let's look at some of the wording on this. We've already talked about the null hypothesis. The null hypothesis, as we mentioned, is symbolized by this H sub 0, H sub nothing, or H sub origin. It is a statistical hypothesis that states that there's no difference between a parameter and a specific value. Or when we get to chapter 9, there's no difference between two parameters. But right now we're going to do the specific value. An alternative or an alternate hypothesis is symbolized by H sub 1 in our book. Some other resources, you'll see the alternative hypothesis with an A. So they'll think of it as O and A, like null or original, and then alternative. But our book uses H sub 1, so we won't worry about the H sub A. But if you ever see that, H sub A is the same thing. So alternative hypothesis is H sub 1. It's the hypothesis that states the existence that there is a difference between a parameter and a specific value. So again, it's that taking the null hypothesis to trial and questioning what it actually says. So the alternative hypothesis is kind of like your charge. You're saying maybe the null hypothesis is that, the average age for a certain thing is 52. And our alternative hypothesis would be the average age is higher than 52, or it's lower than 52, or it's just not equal to 52. That would be your charge. You're coming out and you're saying, I don't believe the null hypothesis. This is what I think is actually happening. So it's like our charge against our poor little null hypothesis that's being taken to trial. Okay, and then our hypothesis test is like our trial. Hypothesis test uses the data obtained from a sample to make a decision about whether the null hypothesis should be rejected, found guilty, or not rejected. And this is done by comparing a test value to a critical value. So the test value is going to be either a z-value or a t-value for our cases, which is the same z-value and t-value that we were using for our confidence intervals. And we're going to take that value and we're going to compare it to a critical value and use that to make a decision. All right. So as I mentioned, that alternative hypothesis, I was describing it as a claim, as a charge. When a researcher conducts a study, he or she is generally looking for evidence to support a claim or a charge. So the claim should be stated as that alternative hypothesis. The alternative hypothesis, as I mentioned, we've got our null hypothesis. That's like the status quo. That's the information that we have right now. And then our null hypothesis, or our alternative hypothesis, is like our charge. What we think is actually, that we're going to take it to trial and try to find evidence for. This is the best practice, is to use that null hypothesis as the claim, as the charge. And so this is the only type that we're going to look at. But just so you know, a claim can be stated as the null hypothesis. But when that's done, the evidence can only support the claim. Well, that's not good practice because the statistical evidence can only support the claim if it's on the alternative hypothesis, as I mentioned up here, where it's on the H sub 1. We can, if we put the claim on the null hypothesis, you can't reject the claim if it's on the null hypothesis. So this just isn't good practice. So the best practice is for this to be the claim. And so that's the type that we're going to see. So when you are doing your homework, it will ask you every time, because there are problems that I could select this way, but on your homework, every time, it's going to ask you which of these is the claim. And all of our problems should be that the null hypothesis is not the claim and the alternative hypothesis is the claim. In my opinion, I don't want to be showing you problems that aren't done in the best practice method. Why would I show you problems that are not done in the form of the best practice? And so I leave those problems out and I only give you problems where the claim is on the alternative hypothesis. If you happen to run across one that I missed, please do let me know. So then, when we're all done, or not when we're all done, but when we start, remember, there's a truth. The null hypothesis is either true or not true. And a decision is made to either reject or not reject based on the strength of the evidence that we find. And so now we're going to practice writing the hypothesis statement. Before we do this, I'm going to kind of jump ahead just a little bit more than we need to, but I kind of want you to understand where we're going. As we mentioned, there's 5 steps in a hypothesis test. So the first step is the hypothesis statement. That's what we're going to work on in the next couple examples. The second step is finding the critical value. That's when we look at the table. Might have said that wrong on the prior slide. So the critical value is what we look up on the table. And then the z or the t value, we use the information that we have and we plug it into the formula. So we do our critical value, we get that off of the table. Then we compute our z or our t value, that's our test value. And we use the formula to find that. And then in step 4, we make a decision to reject or not reject. And then we make kind of like a final conclusion statement. So those are the 5 steps. And what we're working on right now in this section, we're just going to work on this first step. Once we've practiced that a few times and get a couple other things out of the way, then in section 8.2, we'll actually do a full 5-step hypothesis test. So right now, this would be just step 1 of our hypothesis test. Okay, so let's look at our first example here. It says, a contractor wishes to lower heating bills by using a special type of insulation. The average of the monthly heating bills is 78. Her hypothesis statement about heating costs would be this. So let's look at this before we look at the answer. So remember that the null hypothesis is supposed to be our status quo. Well, the status quo is that heating bills have an average of 78. That's our status quo. Past information tells us the average of heating bills should be 78. We're saying, this researcher is saying, that they believe the mean will be less than 78 with the new information. So again, it's not necessarily that the information that we have with the null hypothesis is wrong or bad. We're just wondering if it has changed because of something that's happened. Sometimes that could be it's changed because of time. So say you have a typical age for people getting married, let's say. You want to test, you have information from 10 years ago and you want to do a new test, or you want to do a test and see if that's remained the same, if the average age is still the same. You may have a medicine that you're giving someone and you want to see what it does to their blood pressure or to their heart rate or to the number of headaches they get or something like that. Also, it could be that you're looking at a subsample and comparing it to a larger population. So for instance, you might want to look at the state of Texas in comparison to a national average of something. Or you might want to look at a specific high school in comparison to the national average. So sometimes it's a subset of a larger set of information that you have, and you want to know, does the smaller subset fit the larger population? So it's not always that we think, but sometimes it is, and sometimes a researcher thinks that prior research was not done well, and they're questioning it. But it's not always the case. Sometimes it's a subset, or time has passed, or something has been done, a treatment has been done. Like in this case, our treatment is our insulation. So that's the hypothesis statement. Our hypothesis statement is that the status quo, the known average for heating bills is $78, and she thinks by putting in the insulation that will lower the heating bills. So that's our null hypothesis and our alternative hypothesis, and together that's our hypothesis statement. You can do this a little bit differently, but in our book, the null hypothesis is always stated using an equal sign. You can, this can be done differently, but we're going to, do the way the book is doing. You can do this with like a subtraction, but we're going to stick with the way the book does it, which is an equal sign. This type of hypothesis statement is called a one-tail left, or simply a left-tailed hypothesis, because we're only interested in one direction. So we're only interested in less than, which is to the left on a number line. So we consider that a left-tailed. It's only one tail because we're only concerned about one direction. And in this case, we're worried about the direction to the left, to the less. So that's considered a one-tail left or a left-tailed hypothesis statement. Okay, now we're going to do another example. We're going to do 3 examples. There's kind of 3 different things that can happen, so we're going to do an example of each. So in this case, we have another one where we have a treatment. So a chemist invents an additive to increase the life of an automobile battery. So the additive is like the treatment. The mean lifetime of the automobile battery without the additive is 36 months. So the status quo is that the battery has a mean life of 36. But the chemist wants to increase the life of the battery. So our alternative hypothesis, the claim or the charge, is that they think with the additive that the mean will get larger than 36. So we're always looking for words like increase, decrease, raise, lower, so that we can see if there's a direction to be concerned about. And in this case, they want to see if the additive is going to increase. So we're going to use a greater than. Greater than 36. Is it going to bring the battery life up above 36 months? And then this is considered a one-tail right or a right-tailed hypothesis test. Because again, we're only concerned about one direction. So up here we were interested in less than, only less than. In this case, we're only concerned with increasing, which is to the right on the number line. So we consider that a right tail. We're only interested in the right tail, the right side of what the additive does to the life. Does it bring it up? That's what the researcher is interested in. All right, and then our last situation that could happen is a medical researcher is interested in finding out whether a new medication will have any undesirable side effects. They're particularly concerned with the pulse rate. So we have a new medication, that's our treatment in this case, and they want to know, is that going to affect the heart rate, the pulse rate rather, of the patients who take the medication? Will the pulse rate increase or decrease after the patient takes the medication? So they don't have a hypothesis about whether it's going to go up or it's going to go down. They just are concerned that it might change, that it might go up or down. So in this case, we don't have a greater than or a less than. We have our known population from past studies as being an average of 82 beats per minute. I guess the pulse rate is the same thing as the heart rate. And then we have, in this case, the researcher wants to know if with the medication, the average will not be 82. They're concerned about whether it goes up or down. We're interested in both directions. And because we're interested in both directions, we call this a two-tailed hypothesis test. We're concerned about both if it goes to the right or if it goes to the left. If it goes above the 82 or below the 82. They're interested in discovering if either of those things happen. So we're interested in both tails or both directions that the heart rate could change. So those are the three different things that could happen. Let's kind of summarize. If it's less than, that's a one tail left or a left tail. If we end up with a greater than in our alternative hypothesis, that's a one tail right, greater than. And if we end up with a not equal sign, then that's a two tail. Now, something else I want to point out, you'll notice that every time these two numbers were the same. We don't have different numbers here. Your alternative hypothesis is based on the null hypothesis, so it's always going to have the same number. Notice here we had 82 and 82. Up here we had 36 and 36. And in the one before that we had 78 and 78. So the first statement is always going to have an equal sign. Okay? These two numbers are always going to be the same. And then this is the only number that you're really making a decision about. That's the one where you have to decide whether it's less than, greater than, or not equals to in the alternative hypothesis. But the null hypothesis is always going to have an equal sign. Okay, so our null hypothesis has an equal sign. Both of them have the same number, and then we have to make a decision for the alternative hypothesis if we're looking at less than, greater than, or not equals. The next term or definition or concept that we need to understand is level of significance. The level of significance, remember we talked about those errors. The level of significance that is stated is the maximum probability of a type 1 error. So when we say the percentage of the level of significance, it's usually with a percent or a decimal, we're saying this is how much chance there is for an error. It's very similar. In fact, it's directly related to when we had confidence intervals. It's just stated in the opposite way. So with the confidence intervals, when we were 95% confident, so I'll show it on the chart when we get to that point, but 95% confidence interval would match with a 5% level of significance. For a two-tail test. Now, why is it only the two-tail? Because remember, with the confidence intervals, we were going up and down. We had a minus and a plus. So the confidence intervals match with the two-tail tests, which go up and down. Now, when you do the one-tail test, then you're taking all of that and putting it to one side, and so that changes. It doesn't match up with the confidence interval. I'll show you when we get to the table. It'll make more sense when if I do it that way. But the 95% confidence interval directly matches with a 5% significance level for a two-tail hypothesis test. An alpha is our type 1 error. So the probability of a type 1 error is called alpha, which is also our level of significance. There is a notation for a type 2 error. That's where we don't find enough evidence even though the null hypothesis was false. But that's the one that's not considered as bad. And a type 2 error is called beta. But we're really not going to work with beta at all. But just so you know, a type 2 error does have a name. It's called beta. But the level of significance is what we talk about when we're doing the hypothesis test, and that's alpha, and that's the probability that we get a type 1 error. Typical significance levels, 0.01, 0.05, 0.10, or 1%, 5%, 10%. And so, for example, if they say we're going to do our hypothesis test with an alpha equal to 0.10, that means we're allowing a 10% chance of a type 1 error. So a 10% chance that we're going to reject a true null hypothesis. Again, it's kind of like the confidence intervals where we have a 95% confidence interval means we're 95% certain that we've captured the true mean or proportion within that confidence interval, but that means there's a 5% chance that we didn't. Okay, so with the hypothesis testing, they just state the chance that it's going to be wrong rather than the chance that it's going to be right, like we did with the confidence intervals. Right. Now, we're going to look at, hold on, let me look just ahead just a second. Okay, so we're going to look at how to find the critical value, or what's known as the critical region. If you remember, that was the second step. So we've done the hypothesis statement. We did up above. That was when we had the H sub 0 and the H sub 1. The null hypothesis, alternative hypothesis, we've already practiced that. Now, in these problems, we're going to look at how do we find the critical value. And then the critical value gives us the critical region. And that's our second step. Our third step, when we get to actually doing the hypothesis test, is going to be finding the test value with the formula. This is from the table. This is from the formula. And then we're going to make a decision, reject or not reject, and then we're going to come to a conclusion. So we're doing this step right now. How do you find a critical value? So the critical value, or very often abbreviated just CV, separates the critical region from the non-critical region. And the critical region, also known sometimes as the rejection region, so critical region, rejection region are the same thing, is the range of values of the test value that indicates that there is a significant difference, and so the null hypothesis is going to be rejected. So if we're in the critical region, we are going to reject. Typically when we draw these, it's the shaded region. So if we draw our critical region, typically the part that's shaded is the critical region. Sometimes it's not shaded in, but if it is shaded, if anything is shaded, it's the critical region that's shaded. And then the non-critical region is the range of values that indicates that the difference was probably due to chance, and so the null hypothesis is not rejected. So this, again, if we're in the critical region, that's like we're going to reject. In other words, we're going to find the null hypothesis guilty. If we're not in the critical region, we're going to not reject. So that is the same as if we came back with a not guilty verdict. We don't think the null hypothesis, we didn't have enough evidence to show that the null hypothesis needs to be rejected. So let's look, this is where we're going to go to our chart. So using the t-distribution table, we're going to find the critical values for these. Now it says the t-distribution table, but we're finding z-values. So we're going to use the t-table, but we're going to go all the way down to the bottom and use that row that has the z's in it. Okay. So the first one they want us to do is a left tail test alpha 0.10. So the problem would be when we get to step 2, we would have had our null hypothesis and our alternative hypothesis, so we would know whether it was left-tailed, right-tailed, or two-tailed. The problem will state what the alpha is. So from the null hypothesis, or from the hypothesis statement, we'll know this. So from our hypothesis statement, we will have determined if we are a right tail, left tail, or two tail. And then the alpha will be given in the problem. So if we had determined that it was a left tail test and we were given in the problem that it was alpha 0.10, how would we find that? Well, I always recommend when you do this second step that you draw a picture. I don't actually check it when I'm checking the test, like on an exam. I don't count it right or wrong if you don't have it, but I always highly recommend it. So what I always say is draw yourself a little normal curve. Doesn't have to be beautiful. It's not for anybody but you. So draw yourself a little normal curve. We know it's left-tailed, so that means the mean's going to be in the middle, and then we're going to have only the left tail. So there's going to be a left tail here. And we're going to be finding a critical value right here. That critical value will tell us everything to the left here is our rejection region, and everything over here is our not reject. So it's telling us where's our reject and where's our not reject. Okay, so let's look at our table. If we pull up our table, we look at it almost identically to what we did when we were doing the confidence intervals. We just have to look at the next rows down. So remember, we were one tail left. All right, so here's our t-distribution table. We know that we are one tail, and we know that our alpha is 0.10. And we will use t-values, but for right now we're just going to do the z-values. So we're going to go all the way down until we get the z-value, which in this case is 1.28. So our z-value for an alpha 0.10 one tail is 1.28. Now, if we look at our picture though, that doesn't quite make sense, because remember, if we standardize this, the mean is 0. So if we're to the left of 0, we need a negative. So we just take that number and we put a negative on it. So 1.28, but because it's left tail, it's going to be negative 1.28. So that's our z-value. Our z-value is negative 1.28. And if our test value comes out below that, we're going to reject. If it comes out above that, we're going to not reject. Let's practice that again. Okay, so on this next one, we have a right-tailed test. Again, that's one tail, just to the right. Our alpha is 0.005. So we're going to make our picture first, start our picture. We know it's a right tail, so we know it's over only on this side. Our shade, and we're looking for this value right here, and if we're above that value, we're going to be in the shaded area, so we would reject, and if we were below that value, we would not reject. Let's look at our table. So our table, again, we're going to look at one tail, 0.005, and then we're going to go all the way down to the bottom. We're just doing z values for now. We will do t values when we get to section 8.3, but for right now we're just going to do the z value. So the z value, z critical value, is 2.576 or 2.58 is how Alex always likes us to answer it. So 2.58, and this time we don't have to worry about the negative because we're on the right side. This would be 0. We're on the right side, so it's positive 2.58. Oh, and also, if you look up here, I mentioned that this one, because it's left-tailed, that would have been one of those alternative hypotheses with a less than sign. Here, this would have been an alternative hypothesis with a greater than sign, because it's a right-tailed. Now, we're going to look up and practice a two-tail. So if you had done your hypothesis statement and had gotten a not equals sign, that would mean it was a two-tailed test. They would give you the alpha 0.02. And how do you find that on the chart? Well, we're going to draw our picture first. It's two tails. So instead of having just one side or the other, we're going to have both sides. So we're going to need a value here, and we're going to need a value here. This area is going to be a rejection region, and this area is also going to be a rejection region. So you're going to reject if you're in here or in here. So reject if you're below this value or above that value. And then if you're anywhere in this not shaded area, that would be a not reject decision. We haven't done any test values yet. We're only doing the critical values right now. But when we get to the whole process, you'll have a test value, and that's how you make your decision. So let's go to our chart, our table. We've got two-tailed alpha 0.02. Okay, so you notice there's another row here that says two tails. So we have to jump down to that row. And it was alpha 0.02. And so we're going to go down, and we can find our critical value of 2.33 if we round to 2 decimal spots. So 2.33. But we need two values, remember. So 2.33 is the right-hand value, and then the left-hand value is negative 2.33. Now I promised I would kind of show you how it matched up with the confidence intervals. So you know how I said that if it was a two-tailed test, it directly matched up with the confidence intervals. So you notice two-tailed 20% is the same as a confidence interval of 80%. Two-tailed 10% is a confidence interval of 90%. So they're like complements of each other up to 100%. And so on. And then you'll notice the one tail, again, because we're only going one direction, then the one tail percentage is half of what the two tail is. So the one tail 10% is the same as a two tailed 20%. And then that goes down all the way. One tailed one-tailed 1% is a two-tailed 2%, get the same numbers. Okay, but because the confidence interval goes both directions, it matches perfectly with the two-tailed test. All right. So now we're going to talk about the hypothesis testing steps, and then I'm going to stop this video with that, and we'll continue in the next video with actually doing the hypothesis statement, or the hypothesis test, the full hypothesis test. But here are the testing steps. We've mentioned them before, but I'll mention them again. So the first step is to state the null hypothesis and the alternative hypothesis, the hypothesis statement. Step 2 is going to be to find the critical values from the table, like we just did. The third is going to be the test value, z value or t value in our case, and this is the one where we're going to use a formula. The formula will look very familiar. In step 4, we're going to make a decision to reject or not reject. And then step 5 is a conclusion or a summary. It says summary here, I said conclusion earlier. And just to reiterate, if the z value is in the critical region, we do reject the null hypothesis. And that means that there is enough evidence to support the alternative hypothesis. So when you're making your decision and your summary, you'll notice here, if it is in, so in the positive verbiage, is, we do, because there is enough evidence. So is, do, is. And then on the alternate side, on the other side, if the z value is not in the critical region, we are going to not reject, don't reject, because there is not enough evidence to support the alternative hypothesis or support the claim. So if we're in the critical region, we do reject and there is enough evidence. Okay? Is, do, is. If it is not in the critical region, we do not reject and there is not enough evidence to support. So it's either all positive terminology or all negative, all not terminology. Always go together. That's once you make this decision, then the other two pieces follow. If it is in the in the critical region or the rejection region, we do reject the null hypothesis. There is enough evidence to support the claim. If it is not in the critical region, we do not reject, and there is not enough evidence to support the claim. All right, I will see everyone back. You should be fine to do section 9.1, or sorry, not 9.1, 8.1 homework if you would like to. I would recommend that actually if you go do that before you come back and watch the next video. And when we come back for section 8.2, we'll do a full hypothesis test.